This is another problem about blood, and it says the amount of heat per second conducted from the blood capillaries beneath the skin to the surface is 240 joules per second. The energy is transferred a distance of 2.0 times 10 to the negative 3 meters, so that's 2 millimeters, through a body whose surface area is 1.6 square meters. Assuming that the thermal conductivity is that of body fat, determine the temperature difference between the capillaries and the surface of the skin. So let's see what is given. First of all, they tell us what the heat is conducted per second, so I'm going to write this as Q divided by T. So that one is given. Then the energy is transferred a distance of 2.0 times 10 to the negative 3 meters. So D is given a distance. And then the area of the skin is given, 1.6 square meters. That's a lot of skin. It's about 17 square feet. Assuming that the thermal conductivity is that of body fat, so that would be implied or given, have to be looked up in the book. So that's the K is given. Determine the temperature difference, delta T, and then there's the question mark. And then, of course, the only equation that applies to that would be the equation for the conduction of heat, which is given then as Q equals, and then Ka delta T times time divided by L. For some reason they always use L for length. I guess they're looking here at rods of a certain length L, but for most cases it's a thickness, and I guess, of course, the distance D here is the same as L over here, and we're supposed to figure out what the temperature difference is. So when I do the algebra on this one here, it's going to be Q over T. Actually, I'm going to redo that because that Q over T is already given, so I'm going to write it separately. This one here is one number given as 240 joules per second, and then times the L or the D, and then divide that by K and A, the A being, so this, the D being the 0.002 meters, the K being given in a table in the book, let's see, other materials, as 0.20 joules per second meters and Celsius degrees, and the A given in the book as 1.6 square meters. Equals, and then of course you're going to come up with Celsius degrees for the answer, and it's going to be in the neighborhood of like 1 to 2 Celsius degrees, and so that's how much warmer the blood is just beneath the skin surface. In fact, this is what I found, just a quick look up. Blood temperature is 41 degrees Celsius, 108 Fahrenheit, always slightly higher than body temperature. Actually, this is higher by about 10 degrees here in the book. Let's see, blood beneath the skin. So these are just beneath the skin, so these capillaries might be different from the average blood temperature, and might be cooler, yet a little bit higher, so around 100 Fahrenheit for the capillaries as mentioned in the problem. This problem is about the skier, and it says, a skier wears a jacket filled with goose down that is 15 millimeters thick. Another skier wears a wool sweater that is 5.0 millimeters thick. Both have the same surface area. Assuming that the temperature difference between the inner and outer surfaces of each garment is the same, calculate the ratio wool to goose down of the heat lost due to conduction during the same time interval. So I'm going to see what is given and what they're asking for. What's given is the thickness D or L, and that is given for both of them, for the wool and for the goose down, and the heat conductivities for either one we just look up in the table. The area actually is not given, so we'll see what happens there. The time, it says the same time interval for both of them and the same area for both of them, so we'll see what happens there. And then what we're supposed to figure out is the ratio of the heat loss to the conductivity. So the heat ratio of the wool versus goose down. So I'm going to write here W and then G for goose, and that's what we're supposed to figure out. Okay, of course, heat conductivity, so I'm just going to write this down. Q equals K A delta T time divided by L, and then I'm going to copy this one here because the first one is for wool and the second one is for the goose down. And then I'm going to write that Q of the wool divided by Q of the goose down is all of this here divided by all of that. Notice that with the same area, that divides out with the same temperature difference. That's what they say, and I forgot to write this down here. So delta T. There we go. So none of these is given, but they're saying that the A, the delta T, and the T are the same for either one of them. So when we determine the ratio between the two, they all divide out, and then what happens is that we have a ratio of the heat conductivities and the thicknesses because they were different from one to the other. So here I would have K over L for the wool times L over K for the goose, and of course that's the reciprocal because we're dividing by the goose down numbers, and then equals, and then as shown here all of these are given, and we come up with a ratio with no units. And I'm not going to calculate it because you can easily calculate it, but when I look at the numbers in the book, then the conductivity for wool is a little bit higher than that for goose down, so it's a little bit worse in insulator than the goose down. So as I said, that's a little bit higher, and then the wool has a thickness that is less than that of the goose down. So taking those two numbers into account, what will happen here is that the ratio here is going to be a number larger than 1, in the neighborhood of like between 5 and 10, I guess, somewhere around there, maybe a little bit less than 5. And that means that through the wool sweater, the heat is conducting more easily, more heat conducts out. And as I said, that makes sense because its conductivity is a little bit higher, so its insulation is worse, and it's thinner than the goose down in this problem. This is the problem about the building materials, and it says 3 building materials: plasterboard with a given K in the problem, brick with another K, and wood with yet another K are sandwiched together as the drawing illustrates. At temperatures at the inside and outside surface are 27 degrees Celsius and 0 degrees Celsius respectively. Each material has the same thickness and cross-sectional area. Find the temperature A at the plasterboard brick interface and B at the brick wood interface. Okay, I will not do the problem the way it's written out, and when I teach this in the classroom I always say that, you know, I'm not really interested in what the temperature is in between here, but what I'm interested is how well do these 3 sandwiched together here insulate. So overall what I'm going to do is I'm going to calculate the so-called resistivity or conductivity of these 3 sandwiched building materials. So I'm going to do the problem differently with a different focus. I guess that could be a little bit bigger. There we go. Okay. What I'm going to determine is what is the overall conductivity. So that means I want to determine a K total or equivalent conductivity of these three materials, and I should specify that a little bit better because the conductivity depends on, well, the building material, but it also depends on the distance of each of these materials. I know they're saying they're of all of the same distance, but I would have to say that under normal circumstances you probably have different distances in between here. So I'm going to include that. I'm going to write what is the K over L of these here, all sandwiched together. Okay, with that I have to look at what is actually happening here. Well, heat of course flows from here to here, but it first has to flow through this one, then this one, and then finally this one. And each of these building materials is trying to resist the heat flow, and that's the word I'm going to use, resistance. If you have seen perhaps in another class on DC physics, or took a very basic electricity class, you would be familiar with resistances in series, and when resistances are in series, then the equivalent resistance looks as such: R1 plus R2 plus R3 plus R4 and so on. So simply add the resistances in a series circuit. The same thing happens with thermal conductivity. After all, heat being conducted sounds almost the same as electricity being conducted. In fact, the equations are the same. So the heat encounters this resistance, and this resistance, the heat flow that is, and therefore we would add the resistances. Now, the way it turns out is that the resistance is what I'm looking at here, but what's given in all these equations here, or in this particular equation, is the conductivity, which of course is the reciprocal of the resistances. So this is the way I can write it. The equivalent resistance then is the equivalent conductivity 1 divided by, because it's the reciprocal of the resistance, and then plus the reciprocals of the others. And as I said, I want to include that L, even though they're implying here that they're all of the same distance, so that actually would divide itself out, but here I want to include it because what if you have some other kind of problem where L is given? I'm sorry. The L's are different from one to the other one that are sandwiched together. So that's what I want to calculate. Yet following with this problem here, let's just assume that L is 1 unit. I don't want to call it 1 meter, but I'm just going to call it 1 unit. May that be a centimeter, or may that be a decimeter, which is 10 centimeters. So I assume that each one of these here is 1 unit for the L, and then we're just going to have ones here, and we're going to calculate. And that means that the resistance, the conductivity for each of these here is given as such in the book. So for the first one, it's 0.3 joules per second meters in Celsius degrees, 0.6 for this one, and 0.1 for this one here. Now, when we put them behind each other, we figure out that the insulation has increased, and that means that the conductivity has to go down. So whatever the result is here for the heat conductivity should become less, because that's the idea behind it. So as I said, the given K's are 0.3, 0.6, 0.1, and when we put them together, the overall result should be less than any one of them, so it should be less than 0.1. Okay, let me plug that into the calculator. As I said, I'm going to keep the L as 1 unit. So I'm going to have 1 divided by the first K, which is the 0.6, then plus 1 divided by, oops, that was actually 0.3, plus 1 divided by the 0.6, there it is, plus 1 divided by 0.1. And again, the 1 is in there because I said the L is a unit of, or has a value of 1 unit. So the right hand side being calculated is going to be 15, but I turn this around. This is the reciprocal, so I cannot compare this one here to any of the ones that are given in the book as KL equivalent. So I again take the reciprocal, KL, and the reciprocal of that 15 is 0.067, which indeed is smaller than any one of the others that are given. So, and then the units on this one here is joules divided by second, meters, Celsius, degrees, and again some kind of unit here for the L here in meters or centimeters or what have you. I have to write that on here too. So this first part here can be readily compared, and as I said, the conductivity went down, which makes sense because we're sandwiching these together in series. The resistance, heat resistance, should move up. By the way, that 15 that I calculated a moment ago of the reciprocal, which actually is the resistance, could be kind of considered an R value. If you want to compare that to the real R value that you find in the store, well, you cannot use metric values here. You would have to get the joules into BTU and the meters into feet and the Celsius degrees into Fahrenheit in order to compare that. And here's the conversion. It's this one right here, the 0.176. So if I take that R value of 15 and I divide that by the 0.17611, I come up with a ridiculously large R value of 85. Notice the units here, the kelvins. It's of course the same as the Celsius degrees. You saw the square meter in there, and then the watt is the same as joules per second, and that is then transferred into these units which are underlying the R value. Now, as I said, I come up with 85 for the R value, so this one is equivalent to the American 85 R value, but remember I said for the L here I'm using an arbitrary 1 unit, and of course if I call that unit 1 meter, that's ridiculously large. So if I instead just use 10 centimeters, which means each one of them is 4 inches wide, then that value I just calculated from 85 is only 1/10 of that, 8.5. And here's a table that you can see some of these R values, 7, 8, 6, 5, 6, so it's kind of in that neighborhood. And lastly, here's actually the equation that I used in this problem, where when you have the multi-layered installation, so sandwiched, you come up with adding the resistances. This is the problem about the lake, and it says a 0.30 meter thick sheet of ice covers a lake. The air temperature at the ice surface is negative 15 degrees Celsius. In 5 minutes, the ice thickens by a small amount. Assume that no heat flows from the ground below into the water and that the added ice is very thin compared to the 0.30 meters. Find the number of millimeters by which the ice thickens. I think they're saying in here that the added ice is very thin compared to the original 0.30 meters, because once you add a few millimeters to that, you actually increase the insulation distance, and so that would change the problem slightly. So I say, you know, it's very thin, and just let's just deal with the 0.30 meters. Okay, this is all I could find, so obviously there's no ice on this lake, but I can make myself a drawing kind of in a cross section. So if I take here, let's say the shape of the lake, and then I put the water surface here, and then here is the water, and now I'm going to put a layer of ice on top. I'm not exactly sure I'm going to do that. Well, let's see, maybe some kind of off-white. Oh boy, this is going to be tough. Oh, it's going to be interesting. Let's see what happens. Yeah, something like that maybe. So there we go, there's the thin layer of ice. And now I would have to say that, changing colors, that here I have the negative 15 degrees Celsius, and then inside the lake here, just right underneath the ice, is 0 degrees Celsius, water. And of course, because there's a colder temperature here, heat will flow out of the water just beneath the ice, flow through the ice into the ambient air, and therefore this here will lose heat, and that water, that liquid water, then will become solid ice, and so it makes a phase change still at the same temperature of 0 degrees Celsius. So inside the ice here you actually have a temperature layering here with the coldest negative 15 on the top and 0 at the bottom of the ice sheet, and then 0 degree water, and then due to the density of water peaking out at 4 degrees Celsius, you actually have layers of 1, 2, 3, and 4 degrees Celsius. So inside a lake that is frozen over, you still have water at the bottom and it's 4 degrees Celsius. By the way, on a lake that is not frozen over, like this one here, you also have the 4 degree Celsius layer at the bottom and then just the warmer water instead on top of it. Okay, I just recorded without actually recording. So I wrote this stuff down here and just talked into microphone with actually not recording. So what I wrote here is that the L is given in the problem as 0.3 meters. The temperature difference from the top of the ice to the bottom of the ice is the 15 Celsius degrees. The time T is given as, let's see, 5 minutes, I believe it's said. Yeah, 5 minutes, which will be then 300 seconds. And then we're supposed to figure out by how much the ice thickens. And then, of course, when I look at these here, that kind of gets me to the equation for heat conductivity. And then I notice there's an A. They don't tell us how big the ice sheet, how big the lake is. So I'm writing this down here without a check mark, but I'm figuring out that somehow it will divide out. We'll see. The K here, of course, is given. That's the conductivity of the ice. Okay, and then pretty much in this equation, yeah, we don't know what the area A is, and they don't tell us what the heat flow is. So we have two variables with one equation, and we really can't do anything at this point. But of course, overall, we're supposed to figure out by how much ice is being produced at the bottom, and that kind of leads us to the second equation. That means that, well, that liquid water becomes solid ice with a certain thickness, and that of course involves the latent heat of fusion for water, and so that is Q times L F times mass, with the LF of course given. I'm going to write this over here, kind of run out of space with my little box. So the latent heat of fusion for water is given, but again the mass isn't given. Well, let's see what's going to happen here in a moment. And of course the variable D is actually not in here. We can reason that these two here will be the same. The heat flow through the ice is the heat that is taken away from a certain amount of water that then will then freeze due to the latent heat of fusion. Okay, how do we get the D in there? Well, notice that the A here is not given, but it kind of gives us the area of the lake here, the area of the ice sheet, and the M, the mass, is not given, which of course is kind of similar to that, the area of the lake or of the ice sheet times the thickness that will actually freeze times the density of the water. Well, there it is. So the mass here is the density of the water times the area of the lake times, or the ice sheet, times the thickness that will freeze now. And when you look at these here, at this one and at this one, that's what I said earlier, probably the area A is going to divide out. So I'm going to set these to equal. So the heat that flows out of a certain amount of water will flow is the same as the amount that actually flows through the ice sheet, and because it has this much less heat available, it will undergo a phase change. So it from liquid water at 0 degrees Celsius it will become solid ice at 0 degrees Celsius. So setting these to equal is then going to look like this: Ka delta T divided by L. This is the thickness of the ice sheet, while the LF here is the latent heat of fusion, and then times the mass, which by now is the density of water times the area times the thickness of the new ice. And then actually I have to take something back. If the density is actually the density of the new formed ice, which is appreciably smaller than that of the liquid water. So that mass here could be the density of the water times the area times the thickness of the liquid water, but that mass then would be the same as saying that this is the density of the solid ice times the same area times the actual thickness of the ice that we're supposed to figure out. So this one actually is the density of the ice, and then we're supposed to figure out what the thickness is with the area dividing out, and this is going to be a long one. So K delta T times T divided by LF and the density rho. And when I calculate that, I look up the heat conductivity of ice, which is given as 2.2 joules second meters per Celsius degree, so 2.2, and then times the temperature difference is 15 Celsius degrees, times the time is 300 seconds, and then divide in parentheses. Oh, I forgot something. I just noticed I forgot that L here. I divided by that LF, but there's still that L. I need it actually right now after I multiplied with the time. So the original thickness of the ice is divided by 0.3. So I put the denominator in parentheses, and then I also have to divide by the latent heat of fusion, which I look up in the previous chapter as being for water to ice, of course, 33.5 10 to the fourth, and I have to divide by the density of ice, and that should be in the chapter on either solids or probably solids, because that talked at some point about density. So you might hear me paging in the background. Let's see. Oh, there it is. I hope. Okay, haven't found it yet. Okay, I only found the values for Young's modulus and so on. Okay, it's in the chapter on fluids. The density of ice is 917 kilograms per cubic meter, so I divide by that one as well. And I come up with 1.07 times 10 to the negative 4, and I'm supposed to write that as in millimeters, so it's going to be 0.107 millimeters So a small fraction of an inch that it freezes over in 5 minutes. And I think we have two significant figures in this problem, so I actually should write that as 0.11. Okay, and here I do want to do a unit analysis to finish this problem. So the K is given in the book as joules per seconds and meters and Celsius degrees, and I better double check that. I don't make a mistake here. Yeah, joules per second, meters, and Celsius degrees. Temperature difference, of course, is given in Celsius degrees. Time, I took the 5 minutes and converted it to 300 seconds. And we can already see that a bunch of stuff is dividing out here. L is given in meters. The latent heat of fusion is given in joules per kilograms. And the density is given in kilograms per cubic meters. And then when we look at all the units, well, the Celsius degrees here divide, the seconds divide here. Let's see, kilograms, here's a kilogram that divides by this kilogram, and there's a joule divided by that joule. And then there is divide by meter, divide by another meter, so that's per square meter, and then divide by the reciprocal of cubic meter, so it's going to be cubic meters, this one here, divided by square meters, which of course is meters. And then they ask us to convert these 0.000107 meters into millimeters, which then of course rounded is 0.11 millimeters. And I just want to show the unit analysis here because I usually leave it out. I usually leave it to you to figure that out yourself. This is the problem on the Sun, and it reads, the amount of radiant power produced by the Sun is approximately 3.9 times 10 to the 26 watts. Assuming the Sun to be a perfect black body sphere with a radius of 6.96 times 10 to the 8 meters, find its surface temperature in kelvins. Okay, there are several things to point out in this problem here. It says the amount of radiant power produced by the Sun is approximately 3.9 times 10 to the 26 watts. That is a measured, respectively computed number, and I show that towards the end of the problem how we actually come up with that. Assuming the Sun to be a perfect black body sphere, and the black body is defined in the text, it says, since the color black is associated with nearly complete absorption of visible light, the term black body, perfect black body, or simply black body is used when referring to an object that absorbs all the electromagnetic waves falling on it. And what it will do to the equation, the Stefan-Boltzmann law of radiation, obviously that's what we're going to use for this problem here, is that the emissivity E comes out to exactly 1, so we don't have to invent some kind of number here for a perfect light body that E equals 1. It's a perfect radiator and a perfect absorber. And let's see, then it says with a radius of 696,000 kilometers, or 696 million meters. And how do we know that? I explain that after I'm done with the problem here as well. Find its surface temperature in kelvins. Notice that they're writing here in kelvins because this is, I believe, in my problem section here, kind of the first equation that involves absolute temperatures, and there I have to change to the absolute temperature scale, which of course is in kelvins. Okay, let's see what is given. They tell us what the power is of that the Sun emits, or the amount of radiant power that it emits, and I would express that as the amount of energy. Usually we use the Q as heat, but here it's the total amount of electromagnetic energy divided by the time, and that would be the power. So this one is given. Joules per second is the same as watts. And then they tell us, yeah, that is perfect black body sphere, so E, the emissivity, is given as 1, and then its radius is given from which of course we can figure out what the area is, and then find its surface temperature. This was all of these were supposed to be a check mark, and then we're supposed to figure out what the temperature is. And of course we're using the Stefan-Boltzmann law of radiation, which says Q equals E times the Stefan-Boltzmann constant sigma times temperature to the 4th power times area times time t. And we're supposed to figure out what temperature T is. So that equals the Q divided by T, which I write separately here because this one we have given as a number, and then times, there's nothing else in the numerator, so I'm just going to write a 1 there. And then of course, as we're solving for T here, we have to divide by everything else, so we have to divide by E, which of course is 1 in our case, then the sigma, which is a really tiny number, and by the surface area A, and of course the T is already attached to this one here. And then we have to take the 4th root of that, and that was supposed to be a 4 again. As usual, the 4 smears into a 9. And then because of the units here, you can see if you do the unit analysis, you will come up with kelvins. And of course the A here is that of a sphere, so you have to look up the surface area of a sphere, which is 4 times pi times the radius squared, and of course the radius is given, and you're going to come up with some number, and it probably is what it says here, except this one here. Oh, this is interesting. Oh, I think this is actually in no, is this in Fahrenheit? No, it's not. This is actually in Celsius, but for some reason they didn't write the Celsius down here. So this one here comes out to 6,000 degrees Celsius, and then if you add 273 to that, given these significant figures here, actually that's virtually the same in Kelvin, 6,000 kelvins, or roughly 11,000 Fahrenheit. So that's kind of the result you have to look for. Okay, I wanted to say a few things about numbers that are actually given in the problem, and this is from my website on astronomy. So here's the web address. I'm going to squeeze this in a little bit more so we can look at everything at once here. First of all, I want to talk about the distance that they tell us. I'm sorry, not the distance, but the radius they tell us in the book. And so here the diameter, which is given in the book as 696,000 kilometers. And then, of course, double that is actually 1.4 million kilometers. I don't know why I wrote down here 1.3 million kilometers. But anyway, in order to figure that out, we would have to do the first thing. First, we're going to figure out what the distance is to the sun, and there are two ways. One is use a radar and propel a radar beam at the sun, and then see how long it takes the radar to return to Earth, and that's 17 minutes. And then of course one way is 8.5 minutes. Multiply that with the speed of light and we come up with a distance of 150 million kilometers. There's a second way of looking at that, and that involves parallax and triangulation. Comes out to the same result. I'm not going to explain that method here at this point. And then the diameter, for the diameter we would need to know what that distance is, the 150 million kilometers. Here it is again. And we have to know what the apparent size is, and that is about 0.5 degrees, half a degree. And then if you do the geometry on that, it's actually relatively simple, that you have an extended object and you have this long elongated triangle, and all you have to do is multiply the 0.5 degrees actually in radians. That's why this conversion is here, going from degrees to radians, and then multiply that with the diameter that was determined over here, and you come up with 1.3 million kilometers, or 800,000 miles. And I guess I can see why this one here is a little bit different from the text value here, because I rounded this one here to 0.5 degrees, half a degree. So that's why this one here, of course, is a little bit off because I only deal with one significant figure. Okay, so that's one of the things you figure out that's given in the book, which is the diameter of the radius of the sun. And then the other thing that we need in here is, actually this is given in the problem, 3.9 10 to 26 watts. But how do we figure that out? How much radiation, how much energy the sun radiates per second? Well, what we do is we measure something called the solar constant, which is the energy received from the sun on Earth, measured on Earth and with satellites, and which is measured as 1,370 watts per square meter. So that means each square meter, each 10 square feet on Earth receive 1,370 joules every second, 1,370 watts. But the Earth intercepts only a small part, so what we do is we multiply the number that we measure by the area of a hypothetical sphere of the radius that we are away from the sun. So if you can imagine a huge spherical surface around the sun where Earth sits on just one point of that sphere, and that's what we have to multiply, because with that entire sphere, that's what we have to multiply that solar constant with, because that would be then the energy that the sun radiates. So when we calculate the surface of this hypothetical sphere, multiply by the solar constant, we indeed come up with the 3.9 times 10 to the 26 watts, which is what was given in the problem. This is the problem about oxygen, and it says a young male adult takes in about 5.0 times 10 to the negative 4 cubic meters of fresh air during a normal breath. Fresh air contains approximately 21% oxygen. Assuming that the pressure in the lungs is 1.0 times 10 to the 5 pascals and air is an ideal gas at a temperature of 310 kelvins, find the number of oxygen molecules in a normal breath. Something about the numbers. They already give us the standard units, so we have volume, pressure, and temperature given, and that sure looks like the ideal gas law, of course. About the numbers themselves, the volume is half a liter, 5.0 times 10 to the negative 4 cubic meters, so half a liter is in the neighborhood of an eighth of a gallon. The pressure here sure sounds like standard temperature and pressure, the normal atmospheric pressure, that is. And the temperature sounds a little bit high. 310 kelvins is 37 degrees Celsius, or in the neighborhood of 105 Fahrenheit. Maybe they mean after the air is in the lungs, it has heated up to body temperature. Even that sounds a little bit high. Well, it's in a neighborhood. So, anyway, maybe they should have used ambient pressure. Anyway, what they give us is the volume, they give us the pressure, they give us the temperature, and that, of course, then says the ideal gas law. They also give us the percent of oxygen that is in a normal breath. And let's see. Yeah, that's it. So all we need is the ideal gas law. PV equals nRT. That's given, that's given, that's given. That is a constant, so it's given anyway. So from that we can calculate the number of moles. Why would we do that? Well, because once we have the number of moles, we multiply that with Avogadro's constant. That gives us the number of molecules, and then we multiply it with the percent of oxygen. It gives us the number of molecules of oxygen, which is what they want us to figure out. So N equals RT divided by PV, and there's nothing to convert here because they give it to us in standard units. So whatever you're going to come up here, a very large number. No, I'm sorry, not a very large number. This is moles. So in the neighborhood of, well, a fraction, a little bit less than 1, in fact less than 0.1, you're going to come up with in moles. But once you multiply that with Avogadro's number, so N times Na, and then times the percentage of oxygen, the 21%, respectively, of course, 0.21, you come up with the number of molecules of oxygen. And that one is a very large number because the Na is 10 to the 23. So here you also expect something like 10 to the 21st or so. This is the problem on Venus, and it says on the sunlit surface of Venus the atmospheric pressure is 9.0 times 10 to the 6 pascals and the temperature is 740 kelvins. On the Earth's surface the atmospheric pressure is 1.0 times 10 to the 5 pascals, while the surface temperature can reach 320 kelvins. These data imply that Venus has a thicker atmosphere at its surface than does the Earth, and that's because the pressure is higher and the temperature is higher. Actually, mostly because the pressure is higher than does the Earth, which means that the number of molecules per unit volume, N over V, is greater on the surface of Venus than on Earth. Find the ratio number of molecules over volume for Venus versus Earth. Okay, let's see. Something about the numbers. It says that the pressure on Venus is 9 million pascals compared to 100,000 pascals on Earth. That means that the pressure on Venus is 90 times higher than it is on Earth. The temperature is 740 kelvins, which puts us in the neighborhood of some 700, no more than that, 900 Fahrenheit. So it's very hot, it's very pressurable or impressible. And one thing they don't mention, there's also acid rain falling down. So quite a hostile environment for Earth's twin. Venus used to be called Earth's twin simply because of its size, and then you have these cloud formations going on there, which kind of makes it look like Earth, but once you're on the surface, whoa, definitely not. So anyway, let's see what they give us, and they give us what the pressure is for both of them. They tell us what the temperature is for both of them. We're supposed to figure out what N over V is. Respectively, the ratio between the two. So I'm going to make a question mark here. And because it says N over V, we can look at the alternate or alternative form of the ideal gas law. A moment ago I wrote down PV equals nRT. Now I'm going to write down PV equals capital N times KT, and what has happened here is that originally I'll just go one problem back. Originally, the number of moles times the ideal gas constant has been substituted by the number of molecules times the Boltzmann constant. It just happens, this K here just happens to have the same name, or for a name for the same physicist as the constant in the radiation law from the last chapter with the sigma, which was called the Stefan Boltzmann constant. This K here is a different one. It's just called Boltzmann constant. And when you look at how large it is, the 10 to the negative 3, that kind of sounds like it's almost a reciprocal of the Avogadro's constant. Not exactly, because the ideal gas constant of 8.314 plays in there too, but kind of in that neighborhood. So pretty small number. Anyway, we're supposed to figure out what N over V is. That way, so N over V equals, therefore, let's see, P over KT for each of them. And then we could calculate that, but basically what they want to know is N over V for Venus versus N over V for Earth. So there's an equal here. I had to think here a moment, going from there to there, how I do the algebra, and that looks correct. Okay, so here we're going to have P over T for Venus times T over P for the Earth. And if you look at that, you can figure out that in the process of dividing this by this, the K divided out, and this one here appears as a reciprocal because this fraction here is in the denominator. So equals, so here you have 9 million divided by 740, I believe it was. And then here it's 320 divided by 100,000, and you come up with a fraction with no units. And that should be in the neighborhood of about 40. That means that the Venus atmosphere is about 40 times thicker than Earth's atmosphere. There's a problem on CO2, and it says, if the translational root mean square speed of the water vapor molecules H2O in air is 648 meters per second, what is the translational RMS speed of the carbon dioxide molecule CO2 in the same air? Both gases are at the same temperature. By the way, if they were not at the same temperature, what would happen in a gas gas mixture is that some of them would be actually too fast, would bump into the others, would speed those up, and therefore become slower, so give off some energy, and the overall outcome is that the temperature equals out to be the same among all the gas molecules. That means the root mean squared speed, and therefore the average energy and therefore the average temperature being all the same for all of the gas molecules, respectively gases, in a mixture. That's why they say the temperature is the same for both CO2 and H2O. Okay, let's see what they have given. They have given the VRMS for H2O, but they want to figure out what it is for CO2, and basically that's it. Then of course they say that the temperature is the same for those, and let's see what we're going to figure out here. Well, this is under the header of the kinetic theory of gases, so we look in there what kind of equations we have, and one of them says that the average kinetic energy is 1/2 mv squared. So it sounds like that it's basically the only equation that one appears, VRMS squared, and that equals, and so we have 3/2 the Stefan Boltzmann constant K times the temperature. And this is the way we should do it for the H2O. Just going to copy this here. I think I need it in just a moment. So for the H2O, we have this one here given as 648 meters per second. The mass of the H2O, well, we just looked that up. It's in the front of the book. What the mass of a neutron or proton is, and multiply that with the number of nucleons that we have. And in H2O there would be 18 of them, 1 each for the H and 16 for the O. So we figure out what the mass is, therefore then we figure out what the temperature is, and then we use the same equation and plug that in then for the CO2. So now we would know what the temperature is and plug it in here, and we know what the mass is for the CO2, where on the CO2 we would have a mass of 44 times the nucleonic mass, because this one each is 16, 2 times 16 is 32, plus the 12 here is 44. Okay. Anyway, actually I'm going to do the problem here. I'm just going to need perhaps a little bit more space. And I set the two equal on the right hand side because it says it's the same temperature, and therefore I'm going to come up with m VRMS squared for the H2O equals m VRMS squared, with very bad handwriting, for the CO2. And as I said, the right hand side equals, of course nothing survives there, and then of course both have a factor of 1/2 which divides, and then I figure out what the VRMS is of the oxygen, I'm sorry, of the CO2. So for the CO2, by dividing by the mass of the CO2 on the other side, so I have the ratio of the masses. So M of the H2O divided by M of the CO2 times VRMS squared. And if you imagine that there's a square here and that there's a square here, and I need to get rid of that square here, I take the square root of the right hand side, which gets rid of the square here, but it introduces a square root right there. Again, I trust that you need to know the algebra on this one here, and then when I plug these in, all I actually need to do is take the 18 that I mentioned earlier, divide by the 44, take the square root, and multiply by the, what was that, 648 meters per second, and I come up with the RMS speed for CO2, which will be less because that fraction here is less than 1, and that makes sense. The CO2 is more massive, and therefore in order to have the same energy, this is what it says here, with the right hand side being the same, the left hand side, the average energy is also the same. So for a molecule that has more mass, the CO2 44 versus 32, it has to have a smaller speed. And then I actually don't need the nucleonic mass because that would divide out anyway once I plug it in here. So all I have to do is the square root of 18 divided by 44, and then I multiply that with the 648, and I come up with an average speed of 414 meters per second. By the way, again, where I came up with the mass numbers is actually on the beginning of the book. It's the back of the book, table of the elements. You look at the mass numbers for, or atomic numbers for oxygen, and which is, I'm sorry, not atomic numbers. Atomic mass was correct. So you look it up for oxygen, which is virtually 16. You look it up for carbon, which is virtually 12. You look it up for hydrogen, which is virtually 1. Even rounded to 2 or 3 significant figures, and yeah, the answer then is 414 meters per second. The reason I put the Earth here is because we have a very thin layer of the atmosphere, and what holds the atmosphere to the Earth is Earth's gravitational force, so that holds it on here. But of course we know that rockets can leave the Earth if they attain a certain amount of speed, and molecules can do the same thing. So if molecules are fast enough, they can actually leave Earth. They can leave the Earth, and that is called the escape velocity. And that escape velocity for Earth that can be calculated from an equation that may or may not be in our book in some other place, and comes out to about 11,000 meters per second. Now look at this result here, 414 meters per second for CO2 and 648 meters per second for the H2O, and we can see that's quite a bit smaller than the escape velocity, and so we're able to retain CO2 and H2O. Of course, that's a root mean square velocity, which is kind of an average velocity, but there are velocities, some molecules that are much faster than that, and that goes with the curve that you find in the Maxwell distribution. So some of them, but very few, may leave Earth's atmosphere. However, if you compare that to H2 molecules, so just hydrogen gas has an atomic mass of 2 compared to the CO2 of 44, so the ratio there is 22, and this of course here implies the square root of that, which means that the root mean square velocity speed of hydrogen is approximately 5 times higher than that, so you come up with 2,000, and that 2,000 meters per second for the root mean square velocity of hydrogen in hydrogen molecules in our atmosphere is large enough that in the past there were enough molecules at a faster speed, that they actually escaped Earth, and then give it enough time, actually all of them pretty much escaped. And that's why we don't find light gases like hydrogen and helium in our own atmosphere, because with their little mass, their root mean square velocity was just too large, and they were able to escape Earth.